Okay, so uh, our topic is Z transform. Okay, and in previous week we have discussed what is the importance of Z transform when we are analyzing discrete time LTI system. I hope you have that understanding. Okay, and also um, uh, we use this definition. This is the Z transform definition. Okay. So we use Z transform to convert discrete time signal. This is the discrete time signal. Okay. Into uh, complex domain, complex domain signal. Okay. This Z will be a complex variable. Okay. So we have convert this xn, that is the time sequence. Okay. So this n is the number of sample number that is related with time. Okay. So we can say that this is a time sequence, and time sequence is converted into a complex domain. Okay. So this Z is a complex variable that is situated in a complex plane. Okay. So sometimes referred as Z plane in Z transform, related with Z transform. Okay. So this is the real axis and this is the imaginary axis. Okay. So Z can be any complex variable in this plane. Okay. Including uh, real value also. Okay. And also 0 and infinity also included for the Z. Okay. Okay. So Z is a uh, complex variable. Okay. So Z is equal to, we can say that it is just like x plus iy. Okay. So this is a real part and this is the imaginary part. Okay. But these are not constant, these are variable. Okay. Uh, okay. So if we get a Z transform of time sequence, then it will become a Z domain signal. Okay. Z domain signal, complex domain signal. Okay. Like this. Okay. And we see that when we find this XZ is a transformed signal, complex domain signal, XZ, okay, XZ for some Z value, okay, some Z value, this XZ have finite value, okay? And for some Z value, this XZ will have infinite value. Okay, finite value means including 0. 0 is also finite value. Okay, and at that, so we said that if XZ has got so I think I have disconnected. Okay, anyway, I will give me a moment. I will change my network. Okay, so it is hard to do with this campus network. Okay, I think now it will be okay. Okay, okay. So f is xz has finite value for some z. Okay, we said that this xz is converge. Okay, converge, and that z value is said to be the ROC, region of convergence. Okay, and for other values that xz has got infinite value, those z values, for those z value, this xz is not exist. Okay. So when we are finding the Z transform, the ROC also very important, and we have to define and we have to find the ROC also. Okay. So we have done some example. Okay. This example we have done. Okay. And I think in yesterday class. Okay. We have done one example. Okay. So so you can see that So you can see that all these sequence are finite sequence, okay? All these are finite sequence. All these are finite sequence, okay? Finite sequence. And in yesterday class, we have found the Z transform of infinite sequence also, okay? So that example is, I will redo it here because Monday students haven't done this, okay? So I will redo it quickly, okay? So we have found the Z transform of UN signal, okay? So this is the unity step signal. This is the unity step signal. We have found the Z transform of this signal, okay? So I will quickly do it, okay? So you know that UN is the unity step signal, okay? So signal is somewhat like this. Here it is UN, okay? So we have one here, okay? And, and we have ones up to infinity, okay? So this is zeroth sample, this is first sample, second, third, so on, up to infinity, okay? So this sequence goes up to infinity, okay? So this is the infinite sequence. This is the infinite sequence, okay? Okay, this is the infinite sequence. Okay, okay, I'm sorry. Now I think now you can see now. Now you can see my writing. Okay. So we are going to find the is a transform of unity step signal. Okay. So yesterday we have done this. Okay. I will redo this because Monday student couldn't do this. Okay. So that is very simple. Okay. That is not much difficult. I will do it. Okay. So this is the unity step signal. It is goes from zeros to infinity. Okay. So the value is 1 for every sample. So that is the unity step signal, okay? So if I use that definition to find the Z transform of UN, okay? So that definition is XZ is we have to get the summation from n from minus infinity to plus infinity, Xn Z minus n. So this is the definition of Z transform, okay? So in this case, XZ is equal to, so this n, so you can see that minus infinity to 0, it is 0, all values are 0, and the sequence is starting from 0 to infinity. So n should be 0 to infinity. So we have un here, z minus n, okay? So if we take, okay, now we have to expand this, okay? We have to expand this. So very simple, okay? So n from 0 to infinity, you have to expand this, okay? So u0, it is 1, okay? 1 is at n, again it is 0, okay? Plus u1, that is 1 again, is at n is 1, minus 1. Plus again u2, when the n is equal to 2, this is u2, that is also 1, okay? So it is 1 is at minus 2, plus when n is 3, okay? So un is also 1 when n is 3, un also is 1. Okay, this when n is equal to 3, u3 is also equal to 1, then n is equal to 3, that means minus 3. So this is up to infinity, okay? So this is the XZ. So you have an infinite sequence, infinite power sequence, okay? So we can get a compact answer for this kind of sequences, okay, using Taylor series, okay, using Taylor series, okay, Taylor series expansion. We have seen this in previous when we are finding Fourier series, Fourier transform, okay. So the corresponding Taylor series expansion is given in our book also, for example, okay. So you can use this Taylor series expansion. Actually, this is a Maclaurin expansion, okay. So, so infinite number of values, we will have this compact sequence, okay, compact solution, okay. But this compact solution is valid if the magnitude of A is less than 1. You have to consider this condition also, okay. So we will try to apply it to our case, okay. Now we have xz, that is 1, z minus 1 plus z minus 2 plus z minus 3, so on up to infinity, okay. So you are given that, okay, you are given that 1 plus a square plus a to the power 3 up to infinity as 1 over 1 minus a, okay. So the magnitude of a should be less than 1. To satisfy this solution, we need to have this condition, okay. We need to have this condition. Magnitude of a should be less than 1, okay. So you have to consider that one also, okay. So now uh, so you can see that these are plus powers, okay, but these are minus value, okay. So we can write this as like this, okay, 1 z minus 1, 1 plus z minus 1, 2 plus z minus 1, 3, so on. We can write this now. Again, we will have this same series, 1 minus 1, 1 minus 1, minus 1, 2 minus 2, minus 1, 3, minus 3, so on. We can get the same value, okay. So using this expansion, using this solution, now we can write this as, okay, this x is a dash, okay. This is the z transform of un as 1 over 1 minus, instead of this a, so this z minus 1 is identical to a, okay. So this will be z minus 1. Okay, so okay. So this is the answer, okay. And this solution is valid if z minus 1, magnitude of z minus 1 is less than 1, okay. So magnitude of z minus 1 should be less than 1 to have this solution, okay. So if this z is not in this range, okay, so this solution will not be a valid one. It will have an infinite value, okay. So this xz is valid if this condition is satisfied only, okay. So you can write this as 1 over z magnitude 1, okay. So you can write that. So you can separate this magnitude 1 and magnitude z, okay. So magnitude 1 is 1 again, okay. Then it is like this, magnitude of z, okay. So for this value, for this z value only, this solution is exists. That means for this range, this z is exist, okay. So this will be the ROC, no? This will be the ROC, because for this z values only, okay, if z values are greater than 1, at that time only the magnitude of z is greater than 1, this xz exist, okay. So this is the ROC, okay. So that is the definition of ROC, okay. So if we mark the ROC in the complex plane, it will be like this, okay. It will be like this, okay. It will be like this. So this is the real axis and this is the imaginary axis, okay. Okay. Now magnitude of z, okay. The magnitude of z means if you have any z value, arbitrary z value here, the magnitude of z means the length from here to here. This length is referred as the magnitude, no? You know the complex number. This R is the magnitude. This magnitude is R, and it is equal to x square y square divided square root. Okay, if this is x and if this is y. Okay, and also using the polar form also you can represent this z. Okay, if this is theta phase. Okay, so z can be represented as R E j theta. Okay, using the polar form, using the Euler formula. Okay, because this is equal to R cos theta plus uh, uh, JR sin theta. This is JR sin theta. Okay, so using Euler formula, you can represent Z as like this. Okay, so this is the magnitude. This is the magnitude of the uh, complex number. Okay, so magnitude means this value. Okay, if this magnitude is 1, okay, so this Z, so this is the Z value that magnitude has 1. Okay, so all the values within this circle, the circle radius should be 1. The radius of one circle, within radius of one circle, the Z magnitude is 1. Okay, for any complex value here, the magnitude is 1. Okay, for any Z value, for any complex value in this circle, okay, in this circle is 1. Okay, so the magnitude should be greater than 1. Okay, so that means greater than 1 means this value, these values. Okay, excluded from this circle. Okay, so these values are the ROC of this case. Okay, so these values, if we have these values, okay, if we have inside this circle any Z value, for that Z value, this solution is not exist. Okay, so XZ also will not exist. Okay, only the value out of this circle. Okay, only the value out of these circles give a finite value for finite value for this compact solution. Okay, so this is the ROC. Okay, we have done this. Okay, okay. Now again I will go to the book. Okay, so we have found it. Okay, then I ask you to, if you can, okay, so try to understand the story of this. Okay, so already we know these things. Okay, most of things already we have done. Okay, for example, this is a finite duration signal. Okay, so that sequence has only plus value. Okay, only plus value. So that sequence is starting from 0. It is somewhat like this. Okay, xn is equal to 1, 2, 3, so on. Okay, and have some finite value. Okay, 10 or 5 values. Okay, and this is the 0th sample. Okay, so if we have this kind of signal, okay, we have found the Z transform. Okay, we have found the Z transform of this kind of signal. Okay, so these kind of so it is just like this kind of signal. Okay, it is just like a signal given in example 1. Okay, so we have found that kind of sequence is a transform of that kind of sequence. Okay, so maybe you can remember that if we have this kind of signal with the finite duration, the ROC is the entire Z plane. Okay, but this 0 is not value. Okay, if the Z is 0, because those have 1 over Z value. Okay, 1 over Z value, so Z is 0. So that XZ will be infinite. Okay, so we have experienced this. Okay, so I think you can understand this story here. Okay, so these are called partial signal, finite duration partial signal, because it is from 0 to infinity. Okay, so this type of signal we referred as partial signal. Okay, and I think we haven't done this kind of example but I think you can understand this, okay? So this is anti-Cauchy standard. That means the signal has the minus samples only, not plus sample, minus sample only. So this is also finite sequence, okay? So it is somewhat like this, okay? So if we are given a sequence like this, maybe 1, 2, 3, 3, something like this, okay? And if this one is the zeroth sample, okay? So these are minus sample, okay? This is the minus 1 sample, this is the minus 2nd sample, this is minus 3rd sample. So your signal will be like this, okay? So here the zeroth sample is 3, minus 1 sample is 3, minus 2nd sample is 2, okay, and minus 3rd sample is 1, okay. So this kind of signal, okay. So if you have find the Z transform, okay, so you know that for this kind of signal you will have this 3 plus, here this is 3, Z minus minus 1, okay. So it will be plus 1, Z1 plus, here this is 2, minus 2 is 2. So Z minus 2 minus minus 2. So it will be Z square plus 1 Z minus minus 1. So it will be minus minus 3. It will be Z3. Okay. So this kind of sequence you will have. So now you can see that if you have Z is equal to 0, you will have XZ is 3. Okay. So it is a finite value. When Z is infinity, XZ will have infinite value. Only if Z is infinity, this XZ will have infinite value. Okay. So that is mentioned here. Entire Z plane except Z is equal to infinity. Okay. And two-sided signal, we have experienced this. Okay. So I think in the examples, those kind of signals are given and we have done. Okay. In the class also. So this kind of signal. Okay. So this kind of signal, for this kind of signal, you can see that both Z minus value and Z plus value are there. Okay. So both 0 and infinity, infinity, those values will give infinite value for XZ. Okay. So for that kind of signal, okay, the ROC is entire Z plane, uh, except 0 and infinity. We have experienced this, okay? So this is a causal, infinite duration causal signal, okay? Right now we have done this kind of signal, this kind of one. UN is example for this kind of signal, okay? So as we see that the Z is beyond a circle, the ROC is beyond the circle, okay? And anti-causal signal we haven't done, okay? But if you find, try to find U minus N is a transform of U minus N. So it will be a anti-causal signal. This is the time reverse signal, okay? UN time reverse signal of unity step signal, U minus N, okay? So try to find the, I will not do it here because it is simple, not much difficult, okay? So try to find the U minus N, okay? Is a transform of U minus N. So this will be anti-causal signal like this, okay? Like this, and you will see that this kind of sequence is this kind of this one, okay? So this is this one, okay? So you can see that the ROC will be inside this circle, not the outside, okay? So vice versa of this case, okay? And if it is two-sided, okay? So two-sided means it is just like this one, okay? UN plus U minus N, okay? So this is two-sided signal. If let's say that this is Xn, so UN plus U minus N, this will be the two-sided signal. And also try to find the Z transform of this one. That is also simple, okay? Not much difficult. Z transform of this one, okay? That is UN plus U minus N, okay? So that will be a two-sided signal. Okay, as I can remember, these signals are referred as non-causal signal. Okay. Mm, I think it is correct. Okay, this is called as non-causal signal. Okay, non-causal signal is two-sided signal. Okay, this plus-sided causal and minus-sided anti-causal. If it is two-sided, it is referred as non-causal, as I can remember. Okay, so you can check it. Okay, so this is one example for two-sided signal, and try to find the Z transform of this one. Then I think you will get this kind of one. Okay, this kind of one. Okay, the ROC will be this kind of one. Okay, so I think now you can understand the story behind this. Okay, so some common sense is given here. Okay, some common characteristics are given. Okay, uh, so I think now it is better to go to the Z transform properties. Okay, so there are several properties we have to sometime we have to use when we are finding Z transform. Okay. Yeah, these are the properties of Z transform. Okay. And okay, I think before starting this property, okay, we will do one example. Okay, we will do one example. Mm, we will take the example from the book. Okay, I think it is very easy. It is easy because okay, so we will try to do this one. Okay, okay, we will try to do this example. Okay, so can you try to find the Z transform of this signal? Can you try to find the Z transform of this signal? Okay, just try it. I will give you 5 minutes and just try it. Okay, just try it. Um, okay, actually, uh, to find the, so actually pair is there, okay? The pair means finding the, okay? So finding the transform and finding the inverse transform. For these two, we have two identities, okay? So that is normally referred as pair, okay? The is a the transform side and inverse transformed side. It is normally referred as pair, okay? So here also, the pair is available actually, okay? So Xn, if you put is a transform, okay? You will have the Z domain value, complex domain signal, okay? So that is the Z transform, okay? And if you put the, if you apply the inverse Z transform, okay? Inverse Z transform, again, you will have a time domain signal, okay? So if you apply Z transform to the time domain signal, it will become a complex domain signal. And if you apply the inverse Z transform to complex domain signal, it will convert to time domain sequence, okay? Time domain signal, okay? So the pair is available, okay? So already you have learned this one element you have learned, okay? So that is that definition, okay? Okay, okay, so this is a transform side, okay? So this is one element, okay? So inverse is a transform is also there, okay? Inverse is a transform is also there. Okay, so here, section 1.2, it show the inverse is a transform, okay? So this is the, this is a transform, and this is the inverse is a transform, okay? This one is the inverse is a transform. So you have a pair actually, okay? So is a transform and inverse is a transform, you have identity, okay? So inverse is a transform more, also you have identity, okay? But the problem is that for Fourier, in Fourier case, okay, and also, yeah, in Fourier analysis, okay, so this inverse Fourier transform is just a integration, okay, normal integration. But in this case, it is not a normal integration. It is, we called as contour integration, okay. So this is, here you can hear contour integral, okay. So that means you have to do the integration in a, with the path, okay, with the path from one complex variable to another complex variable. You have to do the integration in this path, okay. So that kind of idea is here, control integrals, okay. So that is somewhat complex, okay. So when we are finding inverse is a transform, we are not going to use this contour integral because it is very mathematically complex, okay. And we have some other techniques, okay. When we are calculating, we are finding inverse is a transform, okay. But we try to use other techniques, okay. We will come to that part, okay. We will come to that part, don't worry, okay. We will learn it, okay. But we don't learn a pair, okay, in here, because this inverse Fourier inverse is a transform somewhat complex than inverse Fourier transform, because we have a special integration techniques here, okay. So we are not going to use this pair when we are going to do the Z transform, okay. But we find inverse Z transform using another techniques, okay. I will explain it, okay. So maybe today, if possible today, I will explain, okay. Okay, so I give you one example, which one I can't remember. This one, no? Okay. Okay, so So have you done this? Okay, okay. So I will do this. Okay. So if you are given this signal, okay, if you are given this signal, if you are okay, we will check. Okay, thank you for the answer. Okay, we will check. Okay, I think it is correct. Your answer is correct. Okay. So we will try to do this one. Okay. Now the signal is an cos omega n an cos omega n Okay. So we are given a signal it's n and cos sorry an cos omega not n un. Okay, this kind of signal is given. Okay, so actually here un indicate the range of the n values. Okay, un indicate the range of the n value. You know that un is somewhat like this. Okay, it is from 0 to infinity. All values are 1. All values are 1. Okay, so if you multiply this sample and this sample, okay, so the cos sample is somewhat like this. Okay, you have some sample like this. Okay, okay, someone you have sample like this. Okay, so you can see that if you multiply this sample with this side sample, those are 0. Okay, so in minus infinity to 0, the value will be 0. Okay, and the value is starting from here. It is from 0 to infinity. Okay, so 0 to infinity, these samples are multiplied by 1. Okay, so the same signal is there. Okay, so in other words, this can in another notation we can show this signal like this. Okay, cos omega n an. Okay, so when n is greater than or equal to 0. Okay, for n values, n is greater than or equal to 0 up to infinity. Okay, so this is, so here we have the value and otherwise you have the 0. That means minus infinity to 0, these values are 0. So this is otherwise. If the n is in this stage, 0 to infinity, so this will be the xn, and minus infinity to up to this level, okay, minus infinity up to -1, it will be 0. Okay, so the same equations are the same representation are okay. Okay, so this un just give us the idea about the range of the signal. Okay, so if it is multiplied by un, it is from 0 to infinity. If it is multiplied by u minus n, it will be 0 to minus infinity. The 0 to infinity value will be 0. It is only exists from this un range. Okay, so that is the idea. Okay. So now, if you use that principal approach, that means the xz is equal to n from minus infinity to plus infinity, xn z minus n. If you use this one, okay, so we will try to apply this one. Okay, so now because it is multiplied by un, the sequence is only exist from 0 to infinity. So minus infinity to 0, it will be 0. So this is exist only 0 to infinity, xn z minus n. Okay, so when n is 0, so it will be a0 cos 0 z also 0 plus when 1 a1 cos omega naught z1 plus a2 cos 2 omega naught Z two, sorry, these are minus, okay, this is minus Z2 plus A3 cos 3 omega naught Z minus 3. So on, you have a value up to infinity, okay. Now, if you are going to find the finite sequence, okay, finite sequence, I don't know it is exist or not, okay. So maybe you can check the Taylor expansion or Maclaurin expansion is there for this kind of series, okay, for this kind of series. Sometime it may be available and sometime using other expansion you can get this, okay. But anyway, you have to do some work here, okay. So we can say that it is somewhat hard to find the Z transform of this kind of signal using a direct method, okay. So it is hard to find the direct Z transform using this direct method, using this one, okay, the principal method, okay. So we have to go for another method, okay. So if we have this kind of inconvenience in finding Z transform, okay, for that one you can use Z transform properties, okay, Z transform properties to calculate the Z transform of this kind of signal, okay. So actually that is the use of Z transform properties, okay. For some for some sequence, it is hard to find the Z transform using a direct method, and you have to use the Z transform properties, okay. So it is happening in Fourier transform also, okay. So we can see that in some, when we are finding some Fourier transform, it is hard to find directly using the using that principal approach, okay. So we have to use a property, okay. So here also you can use a property, okay. Actually, you can use the linear property, okay. So the linear property is given here, okay. So that is one property we are going to use, okay. One property we are going to use, okay. Linearity property, okay. So this linearity property is said like this, okay. So if you have x1n, so these are the notation, okay. If x1n is a transform is x1 z. If x2n is a transform is x2 z. If you have a1 x1n sequence plus a2 x2n sequence, the z transform will be addition of this two Z transform multiplied by the corresponding multiply, okay. And ROC is given as the intersection of, at least the intersection of ROC1 and ROC2, okay. So the ROC, sometime you have to find using the Z transform, okay. So here the ROC may be changed, okay, maybe not, okay. So here it is say that at least, okay. So sometime another value also may be applicable, maybe in ROC, okay. So it just approximate the ROC here in properties, okay. So sometimes the in properties also ROC is defined exactly, okay. But in most cases, it is not defined exactly, okay. For uh, linear properties also, ROC is not defined exactly, but it just give a sense, it just give a hint, okay. Okay, so we will try to use this property to find the Z transform of this signal, okay. Z transform of this signal, okay. So again, I will write this signal xn is equal to an cos omega n un. Okay, so this is the signal. Okay, so I can use this. I can use Euler formula to write this signal as a complex exponential terms. Okay, so I will have an e to the power j omega naught n okay, plus an e to the power minus j omega naught n, okay. So un is there, okay. So I will not put un, okay. So this sequence is valid from 0 to infinity, okay. So that is the idea of this un, okay. This is from 0 to infinity, okay. So I can write like this, okay. So then it is like this, okay. No, I will write the un also here. I will write the un also here, and so maybe it will be easy, okay. So now xn is like this, okay. An e to the power j omega naught 10 un plus an e to the power minus j omega naught n un. Okay. So actually you have found the uh, in Z transform of UN. Okay, so it is somewhat like this. Okay, so you have found the Z transform of UN. Okay, so you will have like this. Okay, xz is equal to 1 plus, okay, 1 plus 1 z minus 1 plus 1 z minus 2, so okay, then you will have the answer 1 over 1 minus z minus 1. We have find this, okay. So if you consider this one, if you see the same uh, way at this one, okay. So in this case, if I take this one, okay, if I take only this one, let's say that it is x2n, okay. If I take that signal separately, okay, don't get confused, okay. I just consider this signal separately, x2n as x2n. So it is an e to the power j omega naught n un. Okay, so if I find the Z transform xz of this signal, okay, so it will be like this, okay. So first, if I use that principal approach, okay, now I can use the principal approach, okay. So that is from minus infinity to plus infinity, xn z minus n. I'm going to apply this one, okay, here, okay. So now you can see that un is here. That means this sequence is from 0 to infinity, and this part is there, an e to the power j omega naught n z minus n. Okay, so this is okay. So if I expand this, I will have, when n is 0, a 0, this one 0, this one 0. So we will have 1 here. Okay, now if 1, I will have a j omega naught. Okay, then I will have a e to the power j omega naught z minus 1 plus, again I will have a e to the power j omega naught 2, here it is a 2 z minus 2, okay. And also I will have a square when n is 3, a 3 e to the power j omega naught 3 z minus 3, so on up to infinity, okay. So you can see that, okay, you can see that, okay. So this is like this, okay, 1 plus, I will take all this one, e to the power j omega naught z minus 1, then this will be 1 plus a e to the power j omega naught z minus 1 square. So I will have a square e to the power j omega naught 2 z minus 2. This one is, I can get this one. And also here, I can see that a e to the power j omega naught z minus 1 square, so on. Okay, so I can use this one, okay. So now you can see that if you can compare this one with this one, instead of z minus 1 here, you will have all these terms, no? All these terms, okay. So here z minus 1 is here, okay. So instead of z minus 1, you will have all this value here, okay. So it's z So xz will be, okay, so xz will be 1 over 1 minus a to the power e j omega naught z minus 1. So this will be the answer. And what is the ROC? Okay, so you can remember that ROC, A should be less than 1. No, A should be less than or greater than. I can't remember. A should be less than 1. Okay, A should be less than 1. Okay, so A should be less than 1. Yes, I'm sorry. Okay. Um, yeah, yeah, okay. I'm sorry. The half should be there, okay? The half value is there, okay? Because using the Euler formula, I have to divide it by 2, and this one also divided by 2, and you can get this half here, okay? And you can get this half here, okay? And here also, this one also, for this one also, you can get half here, okay? And the half value is there, okay? 1 over 2, half value is there. And in this case, so also, the half value is there, okay? So it will be 1 over 2, 1 minus a to the power e omega, e to the power j omega naught z minus 1, okay? So this is the half is there, okay? I'm sorry. Thank you, okay? And to exist this xz, a should be less than 1. Okay, so this is the a value here. Okay, so a to the j omega naught, a e to the power j omega naught z minus 1 magnitude should be less than 1. Okay, so a e to the power j omega naught magnitude is divided by z magnitude is less than 1. Okay, so what is the magnitude of this one? What is the magnitude of this one? Can anyone guess? Can anyone guess? So you can see that this is also a, yes, very good. Okay, so you can see that this is a complex number. No, this is the complex number polar form. Okay, and this will be the phase, and this will be the magnitude. Okay, so magnitude of this term is E. Okay, so this is the magnitude A. Okay. So the Z should be less than A. Okay, so this is the ROC. Okay, this is the ROC. Okay, so in the same manner, you can find the Z transform of this one, Z transform of this one. Okay, so that is okay. So that will be x, let's say that this is x1 is as, this is x2 is as, that will be as the same manner half, okay, 1 over 1 minus a e to the power, instead of this j omega naught, it will be minus j omega naught is at minus 1, okay, like this, okay. And ROC will be same thing, okay, because e to the power minus j omega naught magnitude also will be a, okay. So the same ROC is there. Okay, this ROC and this ROC same. Okay, so according to the linear properties, okay, so if we have separately found the uh, Z transform of this term and this term, we can add them together. Okay, we can add them together without problem. Okay, so the total Z transform will be addition of this x1 is then plus x2 is. Okay, so that is how we can find the ROC. Okay, so this ROC will be this one in the both case. Okay, okay, so we can find, we can check it. this one, no? Okay. Okay. So you can see that. Okay. So okay. So so in this case, okay, in this case the answer is given. Okay. So you can add them together. Okay. Uh, so if you add them together, okay, so you can see that if you add them together, you will have, okay, you have to get the common denominator. Okay. You have to get the common denominator. So that will be 1 minus a e to the power j omega naught. Okay. E to the power j omega naught z minus 1. Okay. Into 1 minus a e to the power minus j omega naught z minus 1. Okay. And you will have here 1 minus a e to the power j omega naught plus 1 minus a e to the power minus j omega naught. Okay. So you can see that again you have uh, a e j omega naught minus a e j omega naught. Okay. A e to the power j omega naught. Okay. So again, using the Euler formula, you can convert this to cos term. So yeah, there's some message from that AI or something. Okay, I don't. Okay, now you can see that. Okay, now again, by getting these separate exponential terms, you can convert them again to the cosine and sine terms. Okay, so here also you can expand this. Okay, you can expand this. This is plus. Okay, this is minus. Okay, then you can expand this. Then you can combine separate different exponential terms, and you can convert it to the cos and sine terms. Okay, so here also the same thing is done. Okay, same thing is done. Okay, and you can see that the upper part is same, no, as we see. Okay, so in this case also. Okay, so uh, so this will be 1 1 2 minus, okay, a e to the power j omega naught plus a e to the power minus j omega naught. So you will have half cos omega naught here. Okay, then the half is there, no? That half, this one is cancelled and this one is cancelled. So you will have 1 minus cos omega naught value. Okay. Okay. This one is there. Okay. So that minus z is also come. Here this minus z, you take as z, then that one also maybe get up. Okay. So anyway, this answer is correct. By simplifying more, you can get this value also. Okay. So that is not necessity. Okay. If you have that compact using the exponential terms also, that will be okay. 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 Now, so that is the use of linear uh, properties of Z transform. Okay. And quickly we will see some other important properties also. Okay. So this time shifting properties also, I think it is somewhat important. Okay. So you can see that if we have Z transform of a signal, okay, let's say that you have Xn, okay, 1, 2, 3, 4, this kind of signal. Okay, we have found the Z transform of this one. Okay, now you are given to find the Z transform. You are given to find the Z transform of X n minus 2. Okay, so this will be the time shifted signal. Okay, so minus 2 means it is shifting in delay side, the plus side, this side. Okay, it is a time delay. Okay, so the so if this one is zero sample here, okay, here the two samples are there, and this will be the zeroth sample now. Okay, so your sequences look like this one. Okay, so you no need to go through the direct approach, principal approach to find the Z transform of this one. Okay, so you can use this time shifting property easily. Okay, if you know the Z transform of this one. Okay, so what you have to do is that you have to multiply it by Z minus K. K is the shifting. Okay, so if it is minus, the minus is there. Okay, so -2, it will be -2. Okay? It is like this. Okay? So that is how you can use time shifting property to calculate the transform of a shifted sequence. Okay, and scaling. This is already we have used scaling. No, this is already we have used. Okay, so for example, we have found the Z transform of UN. Okay, okay, we will have 1 over, we got it as 1 over 1 minus Z minus 1. Okay, so if we have ANUN type 1, okay, so this is scaling. Okay, this is we call this scaling in Z domain, because this Z is scaled. Z is multiplied by a value. Okay, so you know the scaling, no? It is somewhat similar to time scaling. Okay, the time value you have to multiply by a multiplier. Okay, so here also this Z should be multiplied by the, if it is AN minus a value. Okay, so you will have 1 over 1 minus, okay, instead of this Z, you have to put a minus Z. Okay, so a minus Z minus 1. Okay, so you will have 1 over 1 minus a Z minus 1. Okay, you should have this one. Okay, check it. We have learned this. Okay, we have used this, I think, for the previous one. For the previous one, we have found the Z transform of exponential terms. Okay, exponential terms multiplied by UN. Okay, so this property also you can use for that one. Okay, this question. For this one, okay, you can use the property. Okay, so you know the Z transform of this one. Okay, UN, and it is multiplied by this one. Okay, now you can see that instead of this one, you will have a to the power E j omega naught 10. Okay, so that is the scaling in Z domain. Okay, and this time reversal also there. I think you can understand that one also. Okay, so I ask you to find the Z transform of U minus N. Okay, so you know the Z transform of UN. Okay, so that will be 1 over 1 minus Z minus 1. Okay, so if you take minus N, okay, if you take minus N, it will be 1 minus 1 minus, so it is minus now. Okay, minus N, reverse signal, so it will be Z minus 1. Okay, so here it will be Z minus 1 minus 1. Okay, so it will be 1 over 1 minus Z. So this will be the Z transform of U minus N. Okay, so I ask you to find the Z transform of U minus N. Check, you will have this one. Okay, and ROC also you can estimate using this one. Okay, so try to do it also. Okay, and I think this one also somewhat important, differentiation in time domain. Okay, differentiation in Z domain. Okay, so for example, if you are asked to find NUN, Z transform of NUN. Okay, so you have found the Z transform of UN, that is 1 over 1 minus Z minus 1. If you ask to find the Z transform of NUN, okay, then what you have to do is, okay, so NXN, Z transform of Nxn is equal to Z transform of Xz is differentiating one time and multiplied by minus Z. Okay. So you have to differentiate this in one time. You have to get D1, 1 minus Z minus 1, dz. You can find this. This is a division. So you can differentiate the division. Then you have to multiply this Z minus 1. Okay. So you will have the answer. Okay. So this one also I think you can understand by yourself. Okay. And convolution property. Okay. Convolution property, I think we have discussed it. Okay. So in convolution property, you can, I told you that actually this property is very important when we are analyzing LTI system, because this convolution for the LTI system, we know that for the output, we have a convolution. The input convolved by the impulse response. That is, we can get the output of the LTI system. Okay. So if you convert that signals into Z domain, into complex domain, so you can see that this convolution is disappear and it will become a multiplication, simple multiplication. Okay. So this transformation will simplify, it greatly simplify the calculation, okay, analysis of the LTI system. Okay. So you can, so we have already discussed the importance of this property, okay, in our class, okay. So I think it is better to do one example using this one, okay, but now time is not enough, okay. We have already ran out of the time, okay. So I think if we have learned these properties, that is enough. Linearity, time shifting, time reversal, differentiation in Z domain, and convolution. Okay. This correlations property is actually mostly important for analyzing when we are analyzing random signals. Okay. But in DSP and signal and system, we are focusing on only deterministic system signal. I explain it in signal and system. Maybe you can remember. Okay. So I think these properties are enough in our level. Okay. So we will do one example related with this property, okay, in our next class, okay. So we will stop now, okay. So please wait. 2 into 1. I can't understand the question. 2 into half is 1. Half into half is 1/4 in, maybe, okay. So I have done a mistake, maybe there when I multiply, no? Okay. So anyway, I just try to, okay, yeah, thank you. Okay. So I just try to give you a thank you for your focus. Okay. So I just give you I just told you that we can get that given answer using this one. Okay. Maybe when I doing the multiplication, here it should be 1/4. No, yeah, correct. Okay. Okay. So just try to simplify by this yourself and try to get that answer, but it is not compulsory. Okay. If you can get the answer up to this level, it will be okay. Okay. Uh, so please wait. Okay, please wait. I will. So give the attendance, and so while you are marking attendance, I will be here. If you have any problem, you can ask. Okay. Okay, please mark the attendance. Okay. While marking the attendance, I will be here for some time. Okay. So if you have any problem, you can ask. Okay.